6 then is our vectors question. Now I'll apologise at the outset for the presentation of this question. I haven't planned how it's all going to look out. It looks okay on a piece of paper, but on the tablet it's going to perhaps look a bit bizarre. So I'm just going to do my best. We might be jumping around a little bit, particularly at the end. So we've been told that the first line passes through this point and this point. So I want to find the vector equation of this line. So let's just put an arbitrary value of A and B out here, just so that we sort of know what we're doing. So we've got a line that passes through those two. So it's supposed to be a straight line, but nonetheless, so we want to know a point, so a position vector. Let's go with the first one, 0, 9, 6, 9, plus some value of a direction vector. So the direction vector is the vector A to B. So imagine you've got your origin out here somewhere, and that's the vector A, that's the vector B. So to go from A to B, we're going down A, up B, or where you're going minus where you've been. So that's going to be so this is the vector AB here. Let's just take our time with it. So AB is found by doing B subtracting A, 0, 6, 9. So you just need to be very, very careful here, as with all of maths really, but with your minuses and things. So 4 minus 0 is 4. 6 minus 6 is minus 12. Minus 11 minus 9 is minus 20. Okay, so that's your vector AB. So that's what AB is equal to. And as I say, my presentation here is not going to be an exam presentation, but it's really important to label every single thing that you find, because you never know when you might want to know what AB is again later on in the question. So now we've got our line equation for line 1 as well as line 2. So line 1 is 0, 6, 9 plus mu, and you can use whatever letter you like, but standard is mu and lambda, minus 20. Okay, so now we can actually get on with part A. So part A says you've got L1 and you've got L2, and we want to know the value of this between them here. So what we do know is we've got the direction vector of L1, which is 4 minus 12 minus 20, and we've got the direction vector of L2, which is 3 minus 5 and 1. So you should recall, or you're going to have to remember, the dot product formula. So A dot B is the magnitude of A, magnitude of B, cosine of theta. Okay, so in this case, let's call A the first, so 4 minus 12 minus 20, and B is the vector. So it's a vector, so we'll just underline it. The vector 3 minus 5, 1. Okay, so vector, 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 vector. Okay, the absolute value then, so the magnitude of something, this is where we do the Pythagoras. So we do 4 squared plus minus 12 squared plus 20 squared. So I'll just quickly do this first one for us so that we've got a bit of an idea of what's going on. Let's bring the calculator into shot. So I've got 16 plus 12 squared, 144, plus 20 squared, which is 400. So the magnitude of this one is root 560. Okay, the second one, I'll just do a little bit faster. So I've got 3 squared, 5 squared, and 1 squared. So 9 plus 25 plus 1, which gives me the absolute value, which gives me 35. Sorry, so root 35 is the magnitude there. Dot product, if you remember, we'll recall A dot B. So this is where we multiply across each of the values and add them together. So multiplying them across, I've got 4 times 3, which is 12, plus minus 12 times minus 5, which is 60, and then plus minus 20 times 1, which is going to give me minus 20. So then I'm going to take our formula here, rearrange it, so it's A dot B over the magnitude of A times the magnitude of B, which equals cosine of theta. And then if we just put all of that into our calculator, so A dot B, which is 12, plus 60 minus 20, divided by the root of 560, multiplied by the root of 35. And your workings really should reflect that. So you're saying that cos theta is equal to 12 plus 60 minus 20, which you can evaluate if you like. So I don't need the absolute symbol. 560 times root 35, and that comes to 13 over 35. Now, because we've put it into our calculator, that 13 over 35 is the fractional value of theta in its lowest terms. So that's a simplified fraction there for us. So 13 over 35 is the first 5 marks for this question. So what I'm going to do now is I'm going to just sort of clear ourselves a bit of space, but keep this workings here in case we have to refer back to it later in the question. Okay, so here's part B then. I've taken L2 from the original question and also L1 that we've already found. So we're asked to show that the lines intersect and to find the coordinates of that intersection. So in order to do that, we're going to set up 3 equations. So 0 plus 4 mu is going to equal minus 1 plus 3 lambda. So that's taking the x coordinates from both the lines. Then we'll do the y coordinates. So 6 minus 12 mu is equal to 5 minus 5 lambda. And then the z coordinates, 9 minus 20 mu is equal to minus 2 plus lambda. So effectively we've got equation 1, equation 2 and equation 3. So remember, to be intersecting we need to solve the first 2 and show that when we substitute it into the third it satisfies. If it didn't satisfy, that would be where the lines were skew. So looking at these 2 equations, 1 and 2, I'm going to solve them simultaneously, and the thing that stands out to me is these mu terms here. So if I do 3 lots of the first, that's going to give me something that I can solve by elimination. So let's times the first one by 3. You could incidentally do this on your graphical calculator using the equation solver, but I'm going to show you how to do it without, but that is always an option if you're proficient with that. So I've times the first one by 3, and I'm just going to put a 0 in there as well, just as a placeholder, just to keep my algebra nice and strong. Don't have to do anything to the second one, that's why it's a good idea to do that instead of eliminating the lambdas. So I've got a plus 12 and a minus 12, so I'm going to add these 2 equations together. So I've got 6 equals 2 minus 3 plus 5 and plus 4 lambda. Okay, so take away the 2, I'll get 4 equals 4 lambda, so lambda equals 1. From there, let's substitute lambda equals 1 into equation 1 before I did any multiplication to it, nice and simple. So 4 mu equals minus 1 plus 3 lots of 1. So 4 mu is equal to 2 minus 1 plus 3. So mu is equal to a half. Okay, so I've got lambda equals 1 and I've got mu is equal to a half. So as I said when we started part B, the final thing to do is to show that they intersect. So to show that they intersect, we're going to sub into equation 3. So effectively you'd be doing a new line, but I'm just going to go over here. Sub lambda equals 1 and mu equals a half into equation 3. So 9 minus 20 lots of a half should equal minus 2 plus 1. I'm just showing I've substituted the things I substitute and usually put in brackets if I remember to do it. So I've got 9 minus 10 equals minus 2 plus 1. So minus 1 equals minus 1. That is true. So therefore L1 and L2 intersect. So that's where we get our first 4 marks, but we're also asked to find the point of the intersection. So to find the point of intersection, we need to substitute either lambda or mu back into the equation of the straight line. So I'm going to substitute them into L1. So let's put mu back into, actually no, let's put lambda into L2 because lambda is equal to 1, so it's nice and easy. So R is equal to minus 1, 5, minus 2, plus 1 lot of 3 minus 5, 1. So minus 1 plus 3 gives me 2. 5 minus 5 gives me 0. Minus 2 plus 1 gives me minus 1. So that is my coordinates for that point. That's a column vector. That's not really a set of coordinates. It did allow that, but the better thing to do would be to say the point of intersection, P, is equal to 2, 0, minus 1, because that's actually giving it as a set of coordinates. Okay. So we've got 2/3 of our marks now, and as I said, I've left all the workings. So here's the workings for part 2. We've also got the workings for part 1 above, and we'll just go up and we'll have a look at part C. So part C is now the sort of the final bit of this, which is probably the most abstract part. It's the bit which, if you've worked on vectors, you probably haven't done a question like this, but you've done parts A and B before. So we're told that we could create this parallelogram. So there's 2 points on line 1. So I'm going to call those the 2 points that we were given, A and B. And there's 2 points on line 2, which I'm going to call C and D. Now in the mark scheme, there's 2 methods for this one. I'm going to show you the first method. It is much quicker. There's less quadratics involved. But both of them should hopefully hold and make sense. So what we just found in part B was this point here, this point in the middle, which is P. Okay, so we've got this point P, which we have its points, let's put them as a column, so 2, 0, minus 1. So what we're going to do here is we're going to look at this problem by saying there's a vector CD here. Okay, the vector that goes from C to D passes through P. It's not massively important at this point. Now that is a vector on L2. So here is L2. So as a result, if you think about what this means, we've got the position vector, which is just somewhere in space, and the direction vector. So we can say that the vector CD is going to be some scalar, some number, which we'll call T, lots of 3, minus 5, 1. Okay, so that vector is just a multiple of this direction vector, and that comes from the definition of the vector equation of a straight line. So we have this value of T, so that's for the vector CD. Now what else are we told? We're also told that AB is 3 times the length of CD. So the vector AB, and I said we'd need to come back to things at some point. We go back to, we've already found that AB had a magnitude of root 560. So I'm just proving that we have already done that. I know it's quite difficult to follow on the video, but that is there. So I'm not going to calculate that again. I know what that is. So that one is root 560. Now we're told that is 3 times the length of a CD. So that is 3 times CD. Okay, and I'm not going to scroll back again, but you can look back at your notes and you'll see that CD is root 35. Or the magnitude of CD is root 35. Now, that's the magnitude of CD, but we know that that's being multiplied by this vector T. So I've written that again, I should have written root 35. So the magnitude of the vector, that bit there, is being multiplied by T, which is subsequently being multiplied by 3. Okay, so what we now have is an equation that's going to allow us to find T. i.e. it's going to allow us to tell us how big the magnitude of CD. So if we rearrange this here, we're going to get root 560 over root 35, which is equal to 3 times T. Now root 560 over root 35, pop that into the calculator, 560 divided by 35, comes nice and roundly to 4. So 4 equals 3T, so T is equal to 4/3. So what this tells me is that the length of CD here is 4/3 times by the vector 3 minus 5, 1. Okay, so that's the length of CD. Now what we want to know is where C and where D are. So if you imagine, if I just zoom in a little bit more here, we're going from P to D. We're going to do that. Okay, we know what P is, and we now know this length, this value of T. So the value of T, which gives us this whole thing, is 4/3. So the value of T for this bit is going to be 2/3, half of the 4/3. So if we come back out again, a bit more, oops, far too much. Get ourselves in all sorts of trouble here, giving everyone a headache that's watching. Okay, we have P, which is 2, 0, minus 1. And we're going to add on to P 2/3, not the full value of T, because that's going to take us all the way up here. Just half the value of T for 3 minus 5, 1. Okay, and then once we actually evaluate this, that's going to give us the value of what I've labelled on there as point D. So that's going to give us the vector D. And symmetrically, if you like, if I subtract 2/3 of the direction vector, that's going to give me my point C. Okay, so all I then need to do is just to work these ones through on my calculator, if you like, and the final solutions come to 4 minus 10/3 and minus 1/3 and 0, 10/3 and minus 5/3. Okay, now again, you probably should write them out as points, because they are points. So D is equal to 4 minus 10 minus the third, and I'll do C as well, but the mark scheme does state that actually they're accepting them as column vectors. Okay, so as I say, this part C is the abstract bit. It's the bit that you possibly haven't seen something like before, but that's how we get our final 5 marks. There is another method which you can, if you want to have a look at the mark scheme, try and work that one through as well and get your head around how that works, because that will help you prepare for any sort of vectors question regardless of what you're asked in your final exam.